Okay, so we'll start this forced vibration with single degree of freedom today. Okay, at any point of time, if it is not audible, please let me know. So, you can write down in free vibration. In free vibration system, a system once disturbed from its equilibrium position executes vibration executes vibration because of its own elastic property. Okay. The system will come to rest the system will come to rest depending upon its damping characteristic. Its damping characteristics. In case of forced vibration, there is an impressed force on the system which keep it vibrating. Example of forced vibration are let's say air compressor, then internal combustion engine, then your machine tools, and various other machineries. Okay. Uh, we'll discuss about forced vibration with constant harmonic excitation. Okay. So, in forced vibration, the response of the system consists of two parts. Okay, what are they? First is your transient response. Transient response. Response means output, okay? In which the system uh, transient response and the system will vibrate with a damped frequency second one, steady state response in which the system will vibrate with the frequency of excitation. Okay. So to draw an example, let's say we have a spring mass damper system. So this is the spring, this is the damper. So let's say mass is m, okay, and one harmonic excitation force F is your F0 sin omega t. This is the external force that we have given to the system. So in response to this force, the system will have a displacement x and it will have a velocity equal to x dot and its acceleration will be x double dot. Am I audible to all of you? समझते लिखुतु. Okay. Now if you draw the free body diagram of this forces acting upon the mass, we have the force that is F0 sin omega t. This is the external force, okay, that we have applied on the system, and the spring force will act obviously in upward direction, kx, and this is the damping force cx dot, okay, and inertia force mx double dot. Okay, now from Newton's second law, so right here, from Newton's second law, we have F0 sin omega t minus cx dot minus kx minus mx double dot is equal to 0. Okay. Or you can say it is mx double dot plus cx dot plus kx is equal to f0 sin omega t. Okay. Now this equation 1 is a linear second order differential equation and the solution has two parts. First, complementary function. First solution will be a complementary function. Okay. Where the transient part will disappear. Okay. And second part is a particular integral known as EI. Okay, particular integral. Solution of this equation. Now, for complementary solution, we have mx double dot plus cx dot plus kx is equal to 0. Okay. The particular solution is a steady state harmonic oscillation having a frequency equal to the excitation, and the displacement vector lags the force vector by some angle. Now let's say the particular solution, let xp particular solution is x sin omega t minus phi. Okay, let's say this is equation 2, where x is the amplitude of vibration, so x dot p will be omega x cos omega t minus phi, okay, which is also equal to omega x sin omega t minus phi plus pi by 2. Okay, we can write in this way. So this is the velocity, and x double dot p is basically omega square x sine omega t minus phi plus pi. Okay. So as complementary solution, xc will disappear, we have m x double dot p plus c x dot p plus k x p will be equal to f0 sine omega t. Okay, so we can write this as your f0 sine omega t minus m x double dot p minus c x dot p minus k x p is equal to 0. Let this be equation 3, where this f0 sine omega t is the impressed force, or external force. This mx double dot p is the inertial force. Kxp is the spring force. Okay. Now substituting the value of x double dot p comma x dot p and xp in equation 3, we have f0 sine omega t minus m times x double dot p. X double dot p value is omega square x sine omega t minus phi plus pi minus your c x dot p. Value is c omega x sine omega t minus phi, okay, plus pi by 2 minus k xp. So xp value is kx sine omega t minus phi is equal to 0. So this is equation 4. Now the vectorial representation of this equation can be done. How? We'll represent like this. We have this y and x coordinate. Okay, so let this as your reference axis. Okay, and this one is a perpendicular axis, and we'll draw like this. Displacement is denoted by x. Okay, then we have f0 sine omega t. Okay, so this will be the force, that is your f0, okay, at an angle omega t. Okay, so and there is a lag between the displacement and the force equal to phi. This is the phase lag. Then you draw a parallel line with x. Let me change the color. Draw a line parallel to the displacement. Okay. And here, sorry. So this will give you this vector. Okay, from here to here will give you your kx, and this vector will be your c omega x. Okay, and the portion from here to here will be your kx minus m omega square x. Okay, and this portion is your m omega square x. Okay, so this is how you can plot the vectorial representation of the graph. Okay, so from the figure you draw it first. Have you completed? So how to interpret this graph? Let's say this is our displacement x. Okay, and at a phase difference of phi, our f0 force, excitation force, is acting. So the total included angle will be how much? It is phi, lagging phi behind. Okay, then from the equation last part you can see we have minus kx sine omega t minus phi. That means this vector kx vector is in opposite direction because it is sine is minus and included angle is omega t minus phi. So we'll draw a line parallel to this displacement line because this angle is now your omega t minus phi. So that's why we got the vector minus kx omega t minus phi. Okay, got me? This line. Now again we have another component, that is minus c omega x sine omega t minus pi by 2. So at a angular displacement of pi by 2, from this kx vector we have c omega x. So that's why this c omega x is at 90 degree to this kx line. Okay, so we got this minus c omega x sine omega t minus pi, sorry, minus 5 plus pi by 2. Okay. Then further we have m omega square x sine omega t minus 5 plus pi. So this one. Okay, this is at 180 degree with this kx vector. So we got 3 kx c omega x m omega square x. Okay, so this is the interpretation of the graph. Okay, now we can write and that from the figure from the figure we have tan phi is equal to c omega x divided by kx minus m omega square x. Okay, kx minus m omega square x. This is the tan phi, or we can say it is c omega divided by k minus m omega square. Now we can simplify this. C omega by k divided by k minus m omega square by k. Okay, so we can write this as, in the numerator we can write this c omega by k as c by cc multiply with cc by 2m multiply with 2m omega by k. ଆମେ ଲେଖିପାରିବା, our equation is c omega by k. Okay, so c omega by k, it is existing, so I added here in c by cc. So to nullify that, I gave cc here, then I have written here 2m. So to nullify this 2m, I have 2m here. So finally I am getting this. Okay, divided by this k by k is 1 minus this will be omega square by omega n square, because k by root over of k by m is omega n, so k by m is omega n square. Okay, so finally we'll get, what is this c by cc? What is c by cc? It is zeta. So I'll write here your zeta and cc by 2m. What is the value? What is cc by 2m? It is omega n. Okay, multiply with 2 omega by omega n square to simplify. So in the denominator we have omega by omega n square. Okay, so this will be equal to 2 zeta omega by omega n divided by 1 minus omega by omega n square. Okay, understood how we derive this? ତମେ ଦେଖିବ derivation ଭଲସେ. Then we have phi, the phase angle. Phi is basically your tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n square. Okay. So this is the phase angle, that is magnitude, and this is phase angle. Okay, so when zeta is 0, omega by omega n is less than 1, phi equal to 0. For zeta any value, omega by omega n equal to 1, phi will be pi by 2. For zeta any value and omega by omega n greater than equal to 1, phi will be pi. So you remember this condition. Okay. So now from the vectorial representation, we have f0 is equal to kx minus m omega square x square plus c omega x square root over kaiki. Now from the figure you can see figure here we have this component is our f0, this one. So this f0 will be this, that is your kx minus m omega square x square minus plus this, that is your c omega x square root over from the triangle you can see here. Okay, so that I have written here. And f0 by k is known as the zero frequency deflection. Okay, x del st, that is zero frequency deflection of the system and this is equal to x. If you take out, we have k by k minus m omega square by k square plus c omega by k square. Okay, so it is basically your x st divided by, bring this x to this side, so we'll have 1 minus omega by omega n square whole square plus 2 zeta omega by omega n the whole square. Okay, so this x st by x is known as your magnification factor. So you remember this relation. Okay, in forced vibration, this is your magnification factor. So your x so if we write in this fashion x by x st, so it will be 1 divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square whole root over. Okay, and at resonance your omega is equal to omega n, so this ratio x by x st will be basically 1 by 2 zeta. Okay, so your magnification factor mo count kar liya. No, sorry, this is not your magnification factor, sorry, 80. This one is your magnification factor. आगे लिख के So this is your magnification factor. Okay, this is your magnification factor x by xst. So at resonance, when omega is equal to omega n, your magnification factor is 1 by 2 zeta. Okay. Now next, uh, now if you write down the amplitude of vibration, amplitude of vibration, that is your x, will be equal to x st divided by 1 minus omega by omega n square. Okay, square plus 2 zeta omega by omega n square whole root over. Okay, and phase lag phi is basically your tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n square. Okay, so you remember this. This is the amplitude of vibration, and magnification factor is x by xst. Now we have the particular solution. Particular solution xp as x sine omega t minus phi. Now substituting the value of x, the value of this x in equation 19 however in above equation we have xp will be x st sine omega t minus phi divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n. Okay, square whole root over. Okay, so this is the particular solution, and in forced vibration this omega d by omega n is equal to 1 minus zeta square root over. Also your omega p divided by omega n is 1 minus 2 zeta square. Okay, where this omega p is the frequency correspond to correspond to peak amplitude. Frequency corresponding to peak amplitude. Okay, so this is all about your forced vibration case. Now suppose a question is given that the damped, write down the question, the damped natural frequency of a system as obtained from a free vibration test is 9.8 Hz. During the forced vibration test, with constant exciting force on the same system, the maximum amplitude of vibration is found to be 9.6 Hz. Find the damping factor for the system and its natural frequency. क्वेश्चन लिखिला समझते Okay, so here in the given data we can write omega p, that is the circular frequency in corresponding to peak amplitude. Omega p is given 9.6 Hz and omega d will be 9.8 into 2 pi. Okay, radian per second, and so this is also 9.6 into 2 pi. You convert this to radian per second. Okay, now we have a relation that omega p divided by omega n is basically 1 minus 2 zeta square root over. Okay, so we can write here that 9.6 into 2 pi, that is we are referring in terms of radian per second, divided by omega n is equal to 1 minus 2 zeta square root over. Okay, and other part is your omega d by omega n is 1 minus zeta square root over. Okay, so that is your 9.8 into 2 pi divided by omega n is 1 minus zeta square. So from these two equations, we can have let's say dividing equation 1 and 2, we have 9.6 divided by 9.8 is equal to 1 minus 2 zeta square root over divided by 1 minus zeta square root over. Okay, so I can write this as 1 minus 2 zeta square by 1 minus zeta square is equal to 0.96 if you simplify, and you will get the value of zeta is equal to 0.196. Damping factor is 0.196. Now substituting the value of zeta equal to 0.196 in any of the two equations, you can find out omega n as 10 into 2 pi, that is 20 pi radian per second. 20 pi radian per second. Okay, you may get this type of question in forced vibration. Now next is forced vibration with rotating and reciprocating unbalance. So here what is the example of rotating and reciprocating unbalance? Electric motor, turbine, okay, and other rotating machineries. So you may note down an electric motor, a turbine, and almost all other rotating machinery have some amount of unbalance, left in them after correcting their unbalance on precision balancing machine. Now let this m0 is an equivalent mass rotating with its center of gravity, center of gravity uh, that is from axis of rotation, from axis of rotation. Okay. The final unbalance is measured in terms of the equivalent mass m0 rotating with its cg at a distance e from the axis of rotation, from the axis of rotation. Here you can send with its center of gravity e distance. Here also it may change, e from the axis of rotation. Now the cg, the centrifugal force generated because of the rotation of the body is proportional to the square of the frequency of rotation. This force is maximum value of the sinusoidal excitation in any direction. Now we'll draw the figure. Let's say we have a rotating element like this. And it is resting on a spring damper system. So let's say this is K, this is C. Mass M is the total mass of the system, and let's say we have the unbalanced mass is somewhere here. Let it be m0, okay, at a distance e from the CG. Okay, this is your CG. As I told, it is at a distance e from the CG. Okay, so the centrifugal force will be m0 omega square e. Okay, and this angle difference is, let's say, omega t. Okay, so you draw the figure first. So you can write here, consider an elastically supported machine rotating at omega radian per second. Let the unbalance mass m0 have an eccentricity e. Okay, and let m is the total mass of the machine, okay, including unbalanced mass m0. K is the spring stiffness, and C is the damping coefficient. Okay, now let the m0 makes an angle omega t with the reference axis at any instant. So the equation of motion in vertical axis is, it will be equal to m minus m0 d square x by dt square plus m0 d square by dt square x plus e sin omega t. Okay, this is the net force minus kx minus c x dot, or we can write that m d square x by dt square plus c dx by dt plus kx is equal to m0 e omega square sin omega t. we can write in this way. Now if you compare the equation, if we compare the equation with the previous forced vibration equation, this F0 is replaced by this value m0 e omega square. Okay. Therefore, the amplitude of steady state, therefore the steady state amplitude is your x is basically m0 e omega square divided by k 1 minus m omega square by k plus c omega by k whole square whole root over. Let's say this is equation 2. And in a dimensionless form, your x divided by m0 m0 square by m will be equal to omega by omega n square, okay, 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square whole root over. So this is equation 3. And the phase lag equation phase lag equation 5 will be tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n square. Okay. This will be equation 4. At low speed, the centrifugal exciting force m0 e omega square is small, and therefore the response curve starts from 0. and at resonance omega by omega n is equal to 1, and this x divided by sorry ଏଠି ଗୋଟେ ଭୁଲ ଅଛି, ଏଠି ଆମର m0 e ଅଛି ନା, m0 e omega square, it is not square, it is m0 e. Okay, you change it, it will be m0 e, not m0 square, m0 e divided by m, so x m0 e divided by m is equal to 1 by 2 zeta at resonance for rotating unbalance. So लिखिल डेरिवेशन टा समझते am I audible to all of you?
Yes, sir.
हाँ डेरिवेशन लिखिल था. So if you plot this relation, change the color. If you plot this relation, you have graph like this. Just a second, na. हाँ भयो. हाँ बोलो. नहीं मु देखिनी केते इची टोटल की. अच्छा भोगर केते अछि. अच्छा मूर्ति ठीक अच्छी आउ कौन रहा कि सेव केते पकई आ से नन्ना को 1000 टंका हमरो सुमन पंडा सर दैछन्ति जे से पैसाटा ऐड हो से पैसाटा ऐड करछन. हाँ ठीक अच्छे ठीक अच्छे. आ से नन्ना को पैसाटा ऐड करछन्ति 1000 टंका. HOD सर ଦେଇଛନ୍ତି ନା ସୁମନ ସर ସେଟା 1000 ଆଡ୍ କରିବେ ଆଉ हाँ ठीक अच्छे ସେଟା କରିକି ତାଙ୍କୁ ଦେଇ ଦିଅନ୍ତୁ ତା ନାଁରେ ଚେକଟା ଲେଖି ଦିଅନ୍ତୁ ମୁଁ ଇନେ ଅଛି ଉପରେ ଗୋଟେ ସାଇନ୍ କରିଦେବେ ଆଉ ତାକୁ କହିବେ କାଲି ସାରଙ୍କୁ ପଇସା ହ୍ୟାଣ୍ଡ ଓଭର କରିବ 1000 କିଏ ସକ୍ଷମ ଆସିଛି ତ ହଁ ଦେଇଦେବେ हाँ सक्षम तमे आज से चेकटा मुझे साइन करदेवी काली एनकेस कर सारिकी सुमन पंडा सर को 1000 फेरे दब हाँ नहीं सब मो ऊपर अच्छी सैंक्शन साइन करदेव हाँ लिखिदेव मुझे साइन कर So if we plot this this is for zeta is equal to 1 for zeta equal to 2 now this coordinate gives you x divided by m0 e by m and this coordinates give you omega by omega n okay so let's say this is 0 1 2 3 4 here it is 1 2 and 3 so basically you have zeta 0 here then you can take another line zeta 0.125 here also zeta 0 zeta 0.125 then zeta is equal to 0.25 here zeta 0.707 okay. So for different value of zeta the relation between these two components that is x by m0 e by m and omega by omega n square is plotted here okay so this plot is basically dimensionless amplitude versus your frequency ratio so have you completed this graph completed Okay, so now we will go to this vibration analysis. Of reciprocating mass. Vibration analysis of reciprocating mass. So we can draw a figure like this. This one is your reciprocating mass m0. Total mass of the system is m k, and we have this angular displacement is omega t, eccentricity is e, distance from the CG, and k is the spring stiffness, c is the damping coefficient. Complete this. You can write here, let m0 is the equivalent mass of reciprocating part, m is the total mass of engine including m0, e is the crank length, L is the connecting rod length. So this one is your connecting rod and this one is your crank. So here the inertial force due to reciprocating mass is basically your m0 e omega square sine plus e by L sine 2 omega t. If E is small compared to L, compared to your L, the second harmonic component may be neglected, means this component may be neglected, and the exciting force becomes uh, m0 e omega square sin omega t, okay, which is same as in case of rotating unbalance. Okay. Therefore, for small e, same vibration analysis is followed in case of reciprocating unbalanced mass. Okay. माने आमे रोटेटिंग अनबैलेंस पई जो फार्मूला यूज करथलु रेसिप्रोकेटिंग पई सेम फार्मूला यूज करलु, provided we are assuming that the crank length E is quite small compared to the connecting rod length. This you might have obtained from dynamics. Dynamics padithu BTech level la this equation we used to obtain. So here neglecting this equal to 0 will have the equation same as that of your first case. Okay, sorry, here it is omega t na, omega t mu chhadi dichi sin omega t. Okay, now suppose a question is given like this: that a system of beam beam sir, suppose कल दे देव सार को पैसा चेक तो तुम ना आस आई कार्ड तुम आधार कार्ड टा नहीं जाइए बस है हाँ beam supports a motor of mass 1200 kg the motor has an unbalanced mass of 1 kg located at 6 centimeter radius it is known that resonance occurs at 2210 RPM. Okay. What amplitude of vibration can be expected at motor's operating speed of 1440 RPM if damping factor is 0.1 and 0. Okay. So basically we have omega by omega n is equal to 1440 divided by 2210 is equal to 0.652. Okay, and m0 by m is 1 by 1200. Okay, and E is given 6 centimeter, so 0.06 meter, and for zeta equal to 0.1, we have the equation x divided by m0 E by m is equal to, तुम्हारा इक्वेशन कौन था एटी is equal to 0.652, okay, the square, that is omega by omega n square divided by 1 minus omega by omega n square, so 0.652 square whole square plus 2 zeta omega n. Okay, so 2 into 0.1, that is 2 zeta into omega by omega n, this is 0.652 square the root over. Okay, because it was x by m0 E by m, okay, is equal to your omega by omega n square divided by 1 minus omega by omega n square the whole square plus 2 zeta omega by omega n square the root over. Okay, from this we obtained. Okay, so if you solve this, you will get x is 0.036 mm. Now for zeta equal to 0, you will have x by 0.06 by 1200 is equal to 0.652 square 1 minus 0.652 square, it will be, your x will be 0.037 mm. Because if zeta will be 0, this term will be 0. Okay, so left is 1 minus omega by omega n square whole square root over, so it becomes 1 minus 0.652 square. Okay, so this type of question will get. Okay, so you try to read this properly. First make a note, then in the next class I'll see your note. Okay, audible?